Good morning, students. Today I am discussing about air standard cycle. Actually, what is the definition of cycle? A cycle is defined as a repeated series of operation occurring in a certain order. It may be repeated by repeating the processes in the same order. The cycle may be imaginary, perfect engine, or actual engine. The former is called ideal cycle and the latter actual cycle. In ideal cycle, all accidental heat losses are prevented and the working substances is assumed to behave like a perfect working substance. Air standard efficiency, actually to compare the effect of different cycles, it is of paramount importance that the effect of the calorific value of the fuel is altogether eliminated, and this can be achieved by considering air, which is assumed to behave as a perfect gas, as the working substance in the engine cylinder. The efficiency of the engine using air as the working medium is known as air standard efficiency. This efficiency is oftenly called ideal efficiency. The actual efficiency of a cycle is always less than air standard efficiency of that cycle under ideal condition. This is taken into account by introducing a new term, relative efficiency, which is defined as actual thermal efficiency by air standard efficiency. The analysis of air standard cycle is based upon the following assumptions. The gas in the engine cylinder is a perfect gas. It obeys the gas laws and has constant specific heats. The physical constant of the gas in the cylinder are the same as those of air moderate temperature. That is, molecular weight of a cylinder of gas is 29. Cp is equal to 1.005 kilojoule per kg Kelvin and Cv, that is 0.718 kilojoule per kg Kelvin. The compression and expansion processes are adiabatic and they take place without internal friction. These processes are isentropic. No chemical reaction takes place in the cylinder. Heat is supplied or ejected by bringing a hot body or a cold body in contact with the cylinder at appropriate points during the process. The cycle is considered closed with the same air always remaining in the cylinder to repeat the cycle. The Carnot cycle. This cycle has the highest possible efficiency and consists of four simple operations, namely isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Isothermal expansion, 1 kg of air is enclosed in the cylinder which is made of perfect non-conducting material. A source of heat H is supposed to provide unlimited quantity of heat. Non-conducting cover sump which is of infinite capacity so that its temperature remains unchanged irrespective of the fact how much heat is supplied to it. The temperature of the source H and T1 the same is of the working substance. The working substance, while rejecting a heat to some S, has the temperature T2 that is the same as that of the sum. Now, following are the four stages of the Carnot cycle. One is the stage 1, line 1 to 2 represent the isothermal expansion which takes place at temperature T1. When source of heat H is applied to the end of the cylinder, heat supplied in this case is given by RT1 log ER, and where R is the ratio of expansion. Stage 2 line 2-3 represent the application of non-conducting cover to the end of the cylinder. This is followed by adiabatic expansion and the temperature falls from T1 to T2. Line 3 to 4 represent the isothermal compression which takes place when some pace is applied to the end of the cylinder. Heat is rejected during this operation whose value is given by RT2 log ER, where R is the ratio of compression or compression ratio. Actually compression ratio, that is the maximum volume by minimum volume. It may be noted that ratio of expansion during isothermal 1-2 and the ratio of compression during isothermal 3-4 must be equal to get a closed cycle. Now, according to law of conservation of energy, heat supplied, that is the work done plus heat rejected. Work done, heat supplied minus heat rejected. Work done, that is equal to RT1 log R minus RT2 log R. Efficiency of the cycle, that is the work done by heat supplied. R log ER T1 minus T2 divided by RT1 log ER. So T1 minus T2 by T1. From this equation it is quite obvious that if temperature T2 decreases, efficiency increases and it becomes 100%. If T2 becomes absolute zero, which of course is impossible to attain, furthermore it is not possible to produce an engine that should work on Carnot cycle, as it would necessitate and the piston to travel very slowly during first portion of the forward stroke isothermal expansion and to travel more quickly during the remainder of the stroke adiabatic expansion, which however is not practicable. A Carnot engine working between 400 degrees centigrade and 40 degrees centigrade produces 130 kilojoule work. Determine the engine thermal efficiency, the heat addition, the entropy change during heat rejection process. Temperature T1 is equal to T2, that is equal to 400 plus 273, so 673 Kelvin. Temperature T3 is equal to T4, that is equal to 40 plus 273, 313 Kelvin. Work product produced W is equal to 130 kilojoule. Engine thermal efficiency, that is equal to 673 minus 313 by 673. So that is the work done by heat added. 0.535 is equal to 130 by heat addition. So heat addition is equal to 130 divided by 0.535, 243 kilojoule. Now, entropy change during the heat rejection process S2 minus S4, S3 minus S4, that is the heat rejected, heat added minus work done, 243 minus 130, so that is equal to 113 kilojoule. Isentropic 673, 313, heat rejected, so that is equal to T3, S3 minus S4, that is equal to 113. S3 minus S4 is equal to 113 by T3, that is equal to 113 by 313 equal to 0.361 kilojoule per Kelvin. 0.5 kg of air ideal gas executes a Carnot power cycle having a thermal efficiency of 50%. The heat transferred to air during the isothermal expansion is 40 kilojoule. At the beginning of isothermal expansion, the pressure is 7 bar and volume is 0.12 meter cube. Determine the maximum and minimum temperature for the cycle in Kelvin. The volume at the end of isothermal expansion in meter cube, the heat transfer for each of the four processes in kilojoule. For air, Cv is equal to 0.721 kilojoule per kg Kelvin. Cp is equal to 1.008 kilojoule per kg Kelvin. Here, m is equal to 0.5 kg. Eta 50%. Heat transfer during isothermal expansion, that is equal to 40 kilojoule. P1 is equal to 7 bar. V1 is equal to 0.12 meter cube. Cv is equal to 0.721 kilojoule per kg Kelvin. And Cp is equal to 1.008 kilojoule per kg Kelvin. The maximum and minimum temperature T1, T2, P1, V1 is equal to m at T1, 7 into 10 to the power 5 into 0.12 equal to 0.5 into 287 into T1. Maximum temperature T1, that is equal to 7 into 10 to the power 5 into 0.12, 0.5 into 287, that is equal to 585.4 Kelvin. So, efficiency cycle T1 minus T2 by T1, 0.5, 585.4 minus T2 divided by 585.4. Minimum temperature T2 is equal to 585.4 minus 0.5 into 585.4, 22.7 Kelvin. The volume at the end of isothermal expansion V2. Heat transfer during isothermal expansion, isothermal and isentropic. P1 V1 ln R m at T1 ln V2 by V1, 40 into 10 cube, 0.5 into 287, 585.4 ln V2 by 0.12, 40 into 10 cube. So ln V2 by 0.12, so that is equal to 40 into 10 cube divided by 0.5 into 287 into 585.4 is equal to 0.476. The heat transfer for each of the processes, each of the four processes. First one is the classification 1 to 2, 2 to 3, adiabatic reversible expansion, 3 to 4, isothermal compression, 4 to 1, adiabatic reversible compression, 0. In a Carnot cycle, the maximum pressure and temperature are limited to 18 bar and 410 degrees centigrade. The ratio of isentropic compression is 6 and isothermal expansion is 1.5. Assuming the volume of the air at the beginning of isothermal expansion 0.18 meter cube. Determine the temperature and pressure at the main point in the cycle, change in entropy during isothermal expansion, mean thermal efficiency of the cycle, mean effective pressure of the cycle, the theoretical power if there are 210 working cycle per minute. Maximum pressure P1 is equal to 18 bar, temperature T1 is equal to T2, 410 plus 273. Isentropic compression V4 by V1 is equal to 6. Ratio of isothermal expansion P2 by V1 is equal to 1.5. Volume of the air at the beginning of isothermal expansion V1 is equal to 0.18 meter cube. Temperature and pressure at the main points in the cycle T1 by T4, so that is equal to V4 by V1 whole to the power gamma minus 1, that is equal to 6 to the power 1.4 minus 1. So that is equal to 0.4, 6 to the power 0.4 equal to 2.05. T4 is equal to T1 by 2.05. So 683 by 2.05. 333.2 Kelvin equal to T3. So P 1 2 2 3 3 4 4 1 1 2 2 3 3 4 4 1 P1 by P4, so that is equal to V4 by V1 whole to the power gamma minus 1, 6 to the power 1.4, so 12.29. P4 is equal to P1 by 12.29, so 18 by 12.29 equal to 1.46 bar. For the isothermal process 1 2, P1 V1 is equal to P2 V2. তাহলে P2 is equal to P1 V1 by V2, 18 by 1.5, that is equal to 12 bar. For isentropic process 2 3, we have P2 V2 to the power gamma is equal to P3 V3 to the power gamma. Air standard cycle P3 is equal to P2 V2 by V3 whole to the power gamma is equal to 12 into V1 by V4 whole to the power gamma. So 12 into 1 by 6 whole to the power 1.4, 0.97 bar. So therefore P1 is equal to 18 bar, P2 is equal to 12 bar, P3 is equal to 0.97 bar, and P4 is equal to 1.46 bar. So T1 is equal to T2, T3 is equal to T4. Change in entropy during isothermal expansion. S2 minus S1 is equal to Mr log E V2 by V1 equal to P1 V1 by T1 log E V2 by V1. 18 into 10 to the power 5 into 0.18 divided by 10 cube to 683 log 1.5. So that is equal to 0.192 kilojoule per Kelvin. Mean thermal efficiency of the cycle, heat supplied, that is equal to Qs P1 V1 log E V2 by V1 T1 S2 minus S1, 683 into 0.192, so 131.1 kilojoule. Heat rejected QR PO P4 V4 log E V3 by V4 by V4, so T4 S2 S3 minus S4, so because of increase in entropy during heat addition is equal to decrease in entropy during heat rejection. So QR, that is equal to 333.2 into 0.192, 63.97 kilojoule. Efficiency Qs minus QR 1 minus 63.97 by 13.11, 31.11, that is equal to 0.512, 51.2%. Mean effective pressure of the cycle, the mean effective pressure V3 by V1 is equal to 6 into 1.5 equal to 9. So Vs is equal to V3 minus V1, 9 V1 minus V1. That is equal to 8 V1 equal to 8 into 0.18 into 1.44 equal to. So PM, that is equal to 0.466 bar. Power of the engine working on this cycle is given by P is equal to 13.11 minus 63.97 into 210 by 60. So that is equal to 234.9 kilowatt. Okay, so that is the power of the engine. Okay, thank you. Okay.